In the rotary engine, the 4 strokes of a typical cycle occur in the space between a 3-sided triangular rotor and the inside of a housing, although the rotary cycle differs from a regular cycle in the duration of the expansion part of cycle, which is of much longer duration. In the basic single-rotor rotary engine, the oval-like housing surrounds a rotor, which is triangular with bow-shaped sides. The shape of the rotor, between the fixed corners, is the minimization of the volume of the combustion chamber, and the maximization of the compression ratio, respectively. The side curve connecting the 2 apexes of the rotor is maximized in the direction of the inner housing shape, with the constraint not to touch the housing at any angle of rotation. The central drive shaft, called the eccentric shaft or E-shaft, passes through the center of the rotor and is supported by fixed bearings. The rotors ride on eccentric integral cranks, with the eccentric shaft or crankshaft. The rotors both rotate around the eccentrics and make orbital revolutions around the eccentric shaft. Seals at the corners of the rotor seal against the periphery of the housing, dividing it into 3 moving combustion chambers. The rotation of each rotor on its own axis is caused and controlled by a pair of synchronizing gears. A fixed gear mounted on one side of the rotor housing engages a ring gear attached to the rotor and ensures the rotor moves exactly 1/3 turn for each turn of the eccentric shaft. The power output of the engine is not transmitted through the synchronizing gears. The force of combustion on the rotor goes directly to the center of the eccentric part of the output shaft. In other words, the bearings. The best way to visualize the action of the engine in the animation seen here is to look not at the rotor itself, but the cavity created between it and the housing. The rotary engine is actually a variable volume, progressing cavity system. Thus, there are 3 cavities per housing, all repeating the same cycle. Note that points A and B on the rotor and the E-shaft turn at different speed. Point B moves 3 times faster than point A, so that 1 full revolution of the rotor equates to 3 revolutions of the output shaft. As the rotor rotates and orbitally revolves, each side of the rotor gets closer and farther from the wall of the housing, compressing and expanding the combustion chamber similarly to the strokes of a piston in a reciprocating engine. The power curve of the combustion stage goes through the center of the offset lobe. While a 4-stroke piston engine makes 1 combustion stroke per cylinder for every 2 rotations of the crankshaft, each combustion chamber in the rotary generates 1 combustion stroke per each drive shaft rotation, or 1 power stroke per rotor orbital revolution, and 3 power strokes per rotor rotation. Power output of a rotary engine is generally higher than that of a 4-stroke piston engine of similar engine displacement, and higher than that of a 4-stroke piston engine of similar physical dimensions and weight. Rotary engines also generally have a much higher redline RPMs than a reciprocating engine of similar power output, in part because the smoothness inherent in circular motion, but especially because they do not have highly stressed parts such as a crankshaft or connecting rods. Eccentric shafts do not have the stress-raising factor of crankshafts. The redline RPMs of a rotary engine is limited by wear of the synchronizing gears. Hardened steel gears are used for extended operation, above 7,000 or 8,000 RPMs. MAZDA rotary engines in auto racing are operated above 10,000 RPM. Racing regulatory bodies in automobile variously consider the rotary engine to be equivalent to a 4-stroke engine of 1.5 to 2 times the displacement of a similar engine. Some racing circles ban it altogether.